We're going to shift gears today from describing constant velocity problems, general speed, distance, time problems, using words to describing them graphically. And by graphically, I mean by showing graphs, by drawing graphs. You see a whole bunch of graphs up on the board right now, but they have one thing in common. They're all position time graphs. Position time graphs will always have position on the y-axis and time on the x-axis. Why? Well, because you guys learned this when we did our lab, right? The y-axis is always listed first. If it's position time, it's got to be position on the y-axis, time on the x-axis. The other reason? Time is the manipulated variable, always position is the responding variable. Manipulated goes on the x-axis, responding goes on the y-axis. Okay, we know that stuff. We talked about that last Thursday when we did our lab. What you might not be familiar with right now is what these graphs, these specific shapes of position time graphs represent. So that's what I want to go through right now. Okay, each of these, I want you to tell me what they represent. Let's go with the first one now. It's a straight line sloping upwards on a position time graph. Tell me what the object in this graph, or the object represented by this graph, is doing. Yep. It is going at a constant speed, yeah. We're going to say constant velocity, actually, because it's position time. If it said distance time, it would say constant speed. Now, having said that, if it's going at a constant velocity, then it means it's not changing direction. And if it's not changing direction, then the velocity and the speed will be the same value. So speed, constant speed could work there. Constant velocity is a better answer, though. What's your question? No, absolutely not. No. Oliver? Okay. What is the second one, Oliver? Good. Yeah. How do you know this is stopped? Well, because the position isn't changing. If the position here is the same as the position here, then the thing has got to be stopped. So you can say stopped, you can say not moving, you could say at rest, a constant velocity of 0 meters per second. Any of those things would work there. What about the third one? Yeah, Matt? No, it's not slowing down, actually. Good guess, but it's not slowing down. Yeah. Yeah, it's moving backwards at a constant velocity still. We're going to say a constant negative velocity. Backwards, I'm not sure is the best way to describe it, but I think you're thinking the right thing. Yeah, I'll describe it a little bit more, and then I'll get you to tell me whether you were thinking what I'm about to say here. When we say backwards, it kind of infers like something's moving in reverse. Like I'm walking, and then all of a sudden I stop, and then I walk backwards. Or I'm driving my car, and all of a sudden I put it in reverse. Okay, that's not what's happening here. I'm going constant velocity in the negative direction. So if positive is Calgary, drive to Calgary. When I come back to Calgary, from Calgary, I'm going in the negative direction. I'm not driving in reverse on my way back from Calgary, right? I'm just coming in the negative direction. And that's what you meant, right? Yeah. You're just going at a constant velocity in the negative direction, the backwards direction. Good. Let me give you another one, actually, before we move on to the last two. What if we see a position time graph that looks like this? What's going on there? Well, that's still a constant negative velocity, but I want you to describe in a little bit more detail to me what's happening there. Ethan, what's happening right here as the object is at, say, 1 second, 2 seconds, 3 seconds, 4 seconds? Okay, so it's going in the negative direction, and it's going in the negative direction back towards the starting point, right? So it's like saying Okotoks is 0.0. I'm in Calgary driving back towards Okotoks. Does that make sense? I've still got a positive position. I'm still north of where Okotoks is, but I'm going in the negative direction back towards the beginning, back towards the 0 point. What happens here? Well, we're still going at a constant velocity in the negative direction, but where am I now? I've passed my 0 point, right? So if Okotoks is my 0 point, here I'm in Calgary driving towards Okotoks at a constant velocity. Here I'm going past Okotoks, still driving at a constant velocity, but now I'm in High River or south of High River. Make sense? So it's this, but it's the interpretation of where we are that's a tiny bit different there. All right. Next one. Tell me what that would represent. If this one is constant velocity, then this one is, John? Aiden, I mean? It's accelerating, yeah. It's speeding up. You can say accelerating, you can say speeding up, you can say increasing velocity, you can say whatever you want as long as it means the same thing. It's accelerating. And finally, what about the last one? It's decelerating. Another word for that is slowing down or negative acceleration. Deceleration, by the way, is a form of acceleration. So when I say right here acceleration, I probably should be more specific. It's a positive acceleration. It's speeding up. Whereas this one is a negative acceleration, or another word for negative acceleration, deceleration. Let me give you one more, actually two more. This one's different. See if you can figure out this one. You got position time, but this time the line is vertical. Well, that's a tough one. Who's got that one? Matt? No, it's not falling. Yeah. No, it's not stopped. Look, the position is changing, right? It's a bit of a trick. No, it can't. How come? Yeah, you can't go from one place, one position to another position without time having elapsed, right? It's impossible. Unless we went through some kind of wormhole or something, right? We have to have time elapsing. So for all practical purposes, it's impossible, okay? So sorry, trick question. That one won't appear on a test. I just wanted to see if you could figure that out. Let's give you one more, though. This one won't appear on a test either. See if you can figure out what's going on in this one. This is the boomerang one. What's going on here? Andres? Why? Two positions at one point in time, yeah. Which means, how did it get to the same point in time? Aiden? Yeah, that's it. Time's going backwards here, right? Look at what's happening. It's curving upwards like in this one, right? So it's accelerating. It's speeding up, it's speeding up, it's speeding up, it's speeding up, and then what happens? It reaches 88 miles per hour, and then it goes back in time. Is that possible? No, as far as we know, it's not possible without a flux capacitor. It's not possible, right? So what happens when we want to start calculating some things, determining some values, not just what's going on in a graph, but rather what's going on with a number attached to it in a graph? I'm going to plot a graph for you, position versus time, and I'm going to make it a bit of an odd shape. Looks like this. So we got three phases going on here, three different stages. The first stage, it's going at a constant velocity. Second stage, it's stopped, and then it's going at a constant velocity again. We're going to make the time here 5 seconds, 10 seconds, 15 seconds. And we're going to make this 100 meters, and we're going to make this 200 meters. We can describe what's happening in each phase here, but can we determine values that are associated with what's happening? Well, let me tell you that to find the position on a position time graph, easiest thing in the world. All you got to do, go up and over. What's the position at 5 seconds? Go up and over. Oh, it's 100. What's the position at 13 seconds? Up and over. It looks to be about 180 meters. Okay, you want to find the position on a position time graph. All you're going to do is go up and over. You want to find the displacement? Well, it depends on how we define displacement, right? How do we define it? Change in position. If you know how to find position, then we should be able to find the change in position. Just get two positions. Go up and over again, and then subtract them. So we'll say up and over times 2, then subtract. Get a position, get another position, subtract the 2 to get the change in position or the displacement. Average velocity, this isn't new either. You want to find average velocity? It's the same way as we have over the last several days, except that it's in the context of a graph here. Average velocity is displacement divided by time. Good news. We just figured out how to find displacement. Displacement is up and over, subtract the 2 of them. Velocity is the displacement that you just found divided by the time. So you could say for velocity, up and over times 2, subtract them, and then divide by the time. And finally, the instantaneous velocity. Well, we should talk about what that word instantaneous means first. Instantaneous velocity is the velocity at a moment in time. I'm walking around the room right now, and my velocity is changing. There is a delta V, a change in velocity. There's also an average velocity. There's also a velocity at every single moment of time. The instantaneous velocity is how fast I'm moving right now, or now. The velocity at a specific moment in time. Now, if you've got a graph that has only straight lines on it, this is easy. The instantaneous velocity will be the same as the average velocity. We'll say it's the same as the average velocity in a specific section. Now, think about what I just said here. If you find the average velocity for section 1, and it's not changing, then the velocity at any moment in time along that stretch will be the same as the average. If you find the velocity anywhere along here, the average velocity for that one, and it's not changing, then the instantaneous anywhere along that path, anywhere in that section, is going to be the same as the average. So you want to get position, go up and over. You want to get displacement, work from position. Do it twice, subtract the 2. You want to get velocity, then you got to get the displacement, and you work from the displacement, divided by time. You want to get the instantaneous velocity, work from the average velocity. Okay, as long as it's a straight line, the average will be the same as the instantaneous at any moment in time. All right, let's have a look at the worksheet that I just handed out to you. We want the front side of it with the example on there. We got a graph that shows a straight line that's sloping downwards, which means it's a constant negative velocity. It's going in the negative direction, but at a constant speed. We want to know the position of the object in the graph at 10 seconds. So what are we going to do? You guys remember how to find position? We just talked about it. Up and over. Good. So we're going to go to 10 seconds. We're going to go up from 10 over. The position at that point is 30 meters. Positive 30 meters. What's the displacement between 0 and 10 seconds? Displacement is defined as, good, it's the change in position. So we're going to get two different positions and subtract them, up and over, and then subtract the 2. So position at 0 seconds is 80, at 10 seconds is 0. The change in position is always final minus the initial. Somebody this morning said, why are we taking the bigger number from the smaller number? Why isn't it 80 minus 30? It has nothing to do with which one's bigger, which one's smaller. We're taking the final and subtracting the initial. Whatever it is, bigger or smaller or otherwise. Final minus initial. Negative 50 meters is our answer. So what's our displacement? 50 meters to the south. Should it be to the south? Yeah, it's going in the negative direction. The average velocity between 0 and 10 seconds. Displacement divided by time. Displacement is negative 50 meters. Time is 10 seconds. Negative 5.0 meters per second, or 5.0 to the south. Or west, I should say. Should be to the west, yeah. The instantaneous velocity at 2 seconds. Hey, what do we know about the object undergoing the motion in this graph? Yep. Perfect. Between 0 and 10, its velocity will be the same. Perfect way to say it. So, if the constant / average velocity between 0 and 10 is -5, then what's the velocity anywhere along that line if the velocity is constant between 0 and 10? -5. So the instantaneous velocity at 2 seconds is -5. What about the velocity at 7 seconds? Same thing, right? -5, because it's -5 everywhere along that stretch. Do not, and this is what some people like to do. They say, oh, I can find velocity at 2 seconds. Let's go up and over. Oh, it's 75 divided by 2. That's wrong. Velocity is never position over time. Velocity is always displacement over time. Okay, we did that here, and we have a value, so let's go with that. Don't ever go up and over divided by time. You guys okay with that? All right, I'd like you to flip over the worksheet and take a look at the 4 questions that appear on that worksheet. We'll give you, I don't know, 5-6 minutes. We'll take a look at question number 1, and then we'll give you a little bit more time. Take a look at question 2, and so on as we go through this worksheet, okay? Okay, taking a look at question number 1 on the back side of your worksheet. It says, what's the position at 7 seconds? How do you do that? This is the easy one, right, Oliver?
Yeah, you just look at your set, like the second.
Yep.
And you go up
Good. So what's the position there? Good. Up and over 30 meters. The displacement between 0 and 5 seconds. Let's get rid of this line now. Displacement? How do we do that again? All right. Okay, so the final at 5 seconds is 30. At 0 seconds, it's 0 because it goes to the origin. So we'd say the displacement there is 30 minus 0 is 30 meters. Good. The average velocity between 0 and 5 seconds. Anybody else on that one? Yep. Good. So the displacement there is 30 meters. Divided by the time is from 0 to 5 seconds is 5 seconds. Some people are asking, well, what time do you use? And from 0 to 5 is 5 seconds. Don't use the time on the bottom of the graph. Use the time that the question refers to, 5 seconds. Gives me 6 meters per second. It's the average velocity between 0 and 9 seconds. This one's tougher. It's displacement over time again. What's the displacement between 0 and 9 seconds? At 9 seconds, we go up and over 30. 0 is 0, so it would be 30 minus 0 over 9. 3.33. Can I do an average velocity there? Does that make any sense to do an average velocity from 0 to 9 when 2 different things are happening? I'm moving at a constant velocity, and then I'm stopped? Sure it does. Sure it makes sense to do that. We're not talking about a constant velocity. We're talking about average. When I'm driving to Edmonton, I almost always make a stop. Okay, stop in Red Deer for a snack or a drink or whatever. Okay, if I was to figure out my average velocity, I'd figure in that time, right? I'd figure in the time that I stopped in Edmonton, or sorry, in Red Deer. So it's not when you're finding average velocity, it doesn't require you to go to constant velocity. Okay? That's why we call it average. What are you going on average? Now, can anybody explain to me why it's a lower value? Why is the average velocity from 0 to 9 smaller than the average velocity from 0 to 5? Yep. No, it's not constant acceleration. 0 to 5 is constant velocity, right? Okay. Yeah, so it's not moving there. So it's like you're losing time there, right? It always frustrates me when I'm trying to make time on a trip. And I like big road trips. I love big road trips. I was telling you guys about the time that I drove across Canada the first time. I've driven to California and Arizona and all kinds of different places. Love the road trips. But I love the challenge of trying to keep an average speed, say of 100 kilometers per hour or whatever. It's just, I don't know, passes time. It's kind of a challenge. It frustrates me when I have to stop because it's like I'm losing time. I feel like I'm stopping for 10 minutes. Oh, that lowers my average speed, right? When I stop, it lowers my average speed. That's exactly what's happening here, right? You obviously just stop for 3 seconds. That lowers the average speed. Okay, what's the instantaneous velocity at 3 seconds? 3 seconds. What do I do here? Let's say at 3 seconds, it's going to be what? It looks like about 18. 18 divided by 3? No. Well, turns out that it works out to be the same answer, but only by coincidence, okay? The instantaneous velocity at 3 seconds is the same as the average velocity between 0 and 5. So it's going to be the same answer as C, which coincidentally is 6 meters per second. But don't say it's 6 because you went up and over and then divided by 3. That doesn't work. The instantaneous velocity at 8 seconds. Here's one for you. Doesn't even require calculation. Andres? Good. Stopped, right? It isn't moving. All right. Let's continue working on questions 2, 3, and 4 on the back side of that worksheet, please.